Hello, grade 12s, and welcome to another lesson of calculus. Today we are going to be looking at evaluating limits. This lesson is split into two parts, so lesson 6 and 7 will both be on evaluating limits. And today's learning goal is that you are going to be able to evaluate limits algebraically through direct substitution, as well as looking at some factoring methods when we have an indeterminate case. So, as a key information, when you are evaluating limits, there's two ways. So either you have a direct substitution, which is what we've been seeing with the limit properties, or sometimes you will have a case where direct substitution will actually give you 0 over 0, and this is called an indeterminate form. And so when we have an indeterminate form, this is undefined, so we can't necessarily solve it, so we need other methods to be able to solve it. So some of those methods include first using factoring techniques. We can also try to find a common denominator, or we can try to rationalize the denominator, or our final way is change the variable. So today we're going to be looking at some of those, and in lesson 7 we'll finish any other methods that we don't cover today. So first, let's review direct substitution, which is what we've been seeing so far. So here we have the function x over x plus 2, and we want to evaluate the limit as x approaches 2. So here, if I just have 2 over 2 plus 2, and remember, this comes from our limit properties where we are just applying this limit to this x and as well as this x, and through direct substitution, we get 2 over 4, which is half. And if you graph the function of f of x is equal to x over x plus 2, you'll see that as x is approaching 2 from either side, we have that the output value is 1 over 2 or half. Now let's look at another example. Here we have some square roots. So again, we're using limit properties to distribute this limit into the square root to reach those values of x. And so through direct substitution, we have 2 minus 1 in our square root, and in our denominator, we have 2 plus 4. So here we have square root of 1, and our denominator is square root of 6. And we can just leave this as 1 over square root of 6. And again, we see that we are actually getting a value for our output. So the limit is defined and we have a value for it. We were able to solve it. Now let's look at this next example. So here, in our denominator, we have x squared minus 3x plus 2. Let's try direct substitution. So here you'll see that we have 4 minus 6 plus 2. This is equal to 0. And let's just check our numerator as well. We have x cubed, so 2 cubed minus 8, which is 8 minus 8. This is also equal to 0. So here we see that we have an indeterminate case of 0 over 0. And so we're not actually able to solve through direct substitution because it's undefined. So we have to factor. So remember here our difference of cubes formula. So when you have a cubed minus b cubed, this can be factored out as a minus b. And then we have a squared plus ab plus b squared. Now, using this, I'm able to factor my numerator here. So here we have a is x and b is 2, so that a cubed minus b cubed is x to the power of 3 minus 8. And so using that difference of cube formula, I have a minus b, which is x minus 2, and then in our other bracket, we have x squared plus 2x plus 4. And that 2x is actually just AB. Please do not confuse this with difference of squares or perfect squares where you have 2AB. Now, in our denominator, I'm also able to factor this. So just remembering our factoring rules, we're looking for two values that have a product of 2 and a difference of -3. And you'll see that this is actually equal to x minus 2 times x minus 1. And we now have an x minus 2 in our numerator and denominator. And really, that was the bracket that was actually giving us those zeros that was giving the indeterminate case. So now we can simplify by canceling those two out. And so we are left with x squared plus 2x plus 4 in our numerator, and in our denominator we have x minus 1. Now we're going to try direct substitution with this new expression. So here we can see that in our numerator, and I'll just solve it for you, we're just doing 2 squared plus 2 times 2 plus 4. Here we have 12. And in our denominator, we just have 2 minus 1, which is just 1. And this is the information here as well. So our numerator, we have 12, and our denominator, we have 1. And now, through direct substitution, I have that the limit as x approaches 2 of this new factored expression is 12 over 1, or 12. And again, if you try to factor this rational function, so the original function, you'll see that we are approaching the value of 12 there. Okay, and just to show you what this looks like graphically, here I've graphed that function for the original function we started with, so x cubed minus 8 over x squared minus 3x plus 2. And we can see that at the value of 2, which is that red line there, we are actually at a value of 12, where you can see on the y-axis. That being said, you will see that there's no point of intersection here shown on Desmos. And I want you to think about why that is. So the reason for that actually has to do with the domain of the original function. So x cubed minus 8 over x squared plus minus 3x plus 2 is actually not defined for x is 2. Because the denominator will actually be 0. So because it's not defined, that's why we also can't do direct substitution. But we were able to see that by factoring methods, we're able to see the behavior of the curve at x is 2, even though it's not defined. Because clearly we see that the curve is approaching 12 from either side, but we just can't do it through direct substitution. Okay, let's look now at another example. So here we have, for part B, even a bigger function. So we have a cubic function in our numerator and in our denominator. And again, here we're going to see that by direct substitution, in your numerator you get 0, and then the denominator you get 0 if you substitute 2 for x. And so again, we can't do direct substitution, we have to factor. Here we're going to actually try, especially because you have 4 terms, we're going to try factoring by grouping. And that's actually a helpful hint when you have cubic or even just generally polynomial functions that have even amount or even terms, even number of terms, you can try to factor by grouping. So here we're going to see that in the numerator, the first 2 terms both have x squared. So if I factor that out, I'm going to be left with x squared times x minus 3. And for the last 2 terms, I have a -4 factor. So if I factor out that -4, I'm also left with x minus 3. And so now we're going to factor x minus 3 as the term itself, and we're left with x squared minus 4 times x minus 3. And I hope you recognize x squared minus 4 as one of our special quadratic functions. It's the difference of squares. And so we can factor that out as well. And that will be given by x plus 2 times x minus 2. And of course, don't forget that x minus 3 that we had originally. Now for our denominator, we're also doing factoring by grouping here as well. So factoring out x squared from the first 2 terms, we're left with x squared times x minus 2. And for the second 2 terms, I just factor out the negative. And the reason for that is because I wanted to get that x minus 2 here as well, so that I can factor out x minus 2. and I'll be left with x squared minus 1. And again, x squared minus 1 is the difference of squares because 1 squared is 1. So we can also factor that to x minus 1 and x plus 1, but at this point, it's not necessary. And I want you to look at the factors for the numerator and denominator and consider why it's not necessary for me to factor that difference of squares. And another hint for you might be consider what our original limit was. So the limit was x approaching 2. And the reason, again, we were getting that indeterminate case of 0 over 0 was because we had that x minus 2 in our numerator and in our denominator, which was giving us that 0. So I already have those factored out and I can cancel them out. So this term of x squared minus 1 is actually not really contributing negatively to my solution. So I can just leave it as is and simplify my work a little. Now, here I'm just substituting those values or those factors into my numerator and denominator to be able to solve my limit. And here we have just our original limit, and we're now equating that to the factored form. And again, I've simplified out, or I canceled out that x minus 2 in my numerator and denominator, and I'm left with x plus 2 times x minus 3 over x squared minus 1. Now here, you'll be able to see that in your numerator, we have 2 plus 2 and then 2 minus 3, which are not going to give me 0. And same with my denominator, I have 2 squared minus 1, which is 3, so it's also not 0. So I can solve through direct substitution, which is what I've done here. And just through some calculations, I'm able to see that my limit is negative 4 over 3. And here I encourage you to try to graph this function as well, and you'll be able to see that as the curve is approaching, on the curve as x is approaching 2, we have that the curve is also approaching negative 4 over 3. And the function is not necessarily defined for x equals 2, but we're able to, again, predict the behavior by factoring and finding the limit. Now let's look at another example where now here we are simplifying rational expressions. So we've been doing that anyways. We've been having polynomials in our numerator and denominator, which makes it rational expressions. So we're just seeing now a different form. Here we have the limit as h is approaching 0, and I wonder if this reminds you of anything we've seen so far. So this should have reminded you of the limits we've seen in our previous lessons, and we're just trying to generalize now our idea for the function f of x is 1 over x. And that's our rational function, the parent function for a rational function. So here, we're going to actually, for our numerator, start with our numerator, and we're going to try to get a better expression there. And we're going to do that by finding a common denominator and trying to simplify. So here, if you find a common denominator, we see that x plus h and x, we have to just multiply them to get x times x plus h. And doing that to the numerator, because the numerators are 1, it's a little bit easy. We have x minus bracket x plus h, and distributing that negative, we're just left with h there. That actually should be a negative h there, again, because of that distribution, which, considering our limit as h approaches 0, it shouldn't matter, but we're going to put it there anyways and see how that makes a difference. Now, I'm just going to fix that over here as well because this should be negative h. So here I've just rewritten that original limit, and we have negative h over x times x plus h. And this 1 over h is just that denominator that I had. I'm just writing it as a fraction here to be able to see it a little visually better. Because here, I hope you can see that we can cancel out this h and h, which again is the reason we are getting an indeterminate case. So if you try to do direct substitution here, we have in our denominator h, which is just 0. So already we know that's not going to work. But now that we factored out that h and canceled it out, we can actually try to solve through direct substitution because we have x times x plus h, and setting h as 0, we're just left with x times x, which is x squared. So we have 1 over x squared by direct substitution. And this should remind you of our limit rules that we saw um, because we've been working with forms like this, just with different functions. Now we have another function, and again, we always check with direct substitution first. But right away, I can see in my denominator x minus 2, and with our limit of x approaching 2, I'm going to actually get 0. So just the fact that my denominator is 0 is enough to tell me that I can't solve this through direct substitution, and I need to do something else. So here, again, try to find a common denominator for the numerator to try to simplify this expression and hopefully be able to factor out that x minus 2. So here, finding a common denominator between 2 and x, our lowest common denominator is just 2x. And in our numerators, we're going to get 2 minus x. And although it doesn't look like it right away, I've factored that negative for you to see. This is that x minus 2 that we were trying to factor out. And now I'm just going to rewrite the limit with this new form. So again, writing that original limit is equal to, now we have negative x minus 2 over 2x. And again, this times this fraction is my denominator of x minus 2. I've just written it as a fraction so I can visualize this a little better. And now I can factor these two out, which again was the term that was making my limit an indeterminate case or an indeterminate form. And now I'm just left with negative 1 over 2x. And here we can just apply direct substitution and we get negative 1 over 4. Now, let's look at one more example. And this is actually another case of solving limits, which was our second case, which was rationalizing the numerator or denominator. Sorry, not our second case, this is our third case. The previous examples were the case of finding a common denominator, which sometimes we have to do that for our numerator, not necessarily the denominator, but it helps simplify your expression so that you're able to actually solve with direct substitution. So now here, again, right away I see x is approaching 0, and I have x in my denominator, which is going to be 0. So this is an indeterminate case, so I can't solve through direct substitution. But here I have also a square root. So that's telling me that, and that will be your hint to rationalize. And here we have to rationalize the numerator because the square root is in the numerator. So if you remember, we have to multiply this by its conjugate, which is going to be x plus 1. So we keep the square root as itself, and we're going to do plus here. And my second term, it was negative 1, so it's just going to be plus 1 now. And our goal with rationalizing was to just multiply by 1, which is actually just the conjugate over the conjugate, which is just equal to 1, which is what I've done here. And now multiplying that through, I'm rationalizing my numerator to get that square root to become x plus 1, just on its own, and I had that minus 1 left. And now in my denominator, I have that same conjugate, but if you look at substituting x approaches 0 for the denominator here, I would just get square root of 1 plus 1 times x. Or again, well, actually, the x we're gonna see that it's going to go away, but that just the conjugate itself would work in my denominator. Now, in our numerator, x plus 1 minus 1 is just x. So really, we had this part equal x, and then I'm just canceling, maybe I'll do a different color, these two x's out so that I'm left with an expression where I'm not going to get an indeterminate case if I substitute x is 0. Now, here, finally, I've just done this direct substitution, so you can see that this new expression, which is the same expression just in a different form, through direct substitution will give me the limit of 1 over 2. So now we're going to try one more example just to wrap up our last method for solving indeterminate forms for this lesson. And I highly encourage you to try this one on your own through use of conjugates and check back to see if your solution matches mine. So here, now I see that my square root is actually in the denominator. And again, we're going to check with direct substitution. We have the square root of 9, which is going to be 3, minus 3 is 0 in our denominator, so it's an indeterminate case. Now we're going to actually rationalize the denominator. And again, remember, we're going to keep that square root of x, and it's going to become plus the second term, which was 3. And if we multiply by square root of x plus 3 over square root of x plus 3, we're going to rationalize our denominator here, and we're going to get x minus 9 in our denominator. And in our numerator, we have that x minus 9, it just stays, and now we have our conjugate of square root of x plus 3. And because it's plus here, now substituting that 9, we're not going to get a 0, so it'll work out. And the term that's actually making it 0 is that x minus 9. We're going to cancel those two out. And now we're just left with square root of x plus 3, which if we try by direct substitution, we just have square root of 9, which is 3, plus 3 is 6. And again, for this one, I recommend that you try to graph both a and b to see what the function would look like, and you'll see that while x is not defined for those values of the limits for the function itself, we can try to determine what value the curve is approaching at those x values to determine the behavior of the curve. And so today you have some practice problems to work on, and check on Google Classroom for any additional tasks that you have to complete. And as always, if you have any questions, don't hesitate to reach out, and I'll see you next class for lesson 7 for our final way to solve or evaluate limits, which is change a variable.